2's the line through the 1's and the line through the 3's. So those three lines are all parallel in the affine model. And then to make it projective, we just meet them at the point. And then similarly, this line square produced the blue, purple, and light blue lines, which met at E2.
Wait, so doesn't this just produce like an affine model that then you make into...
Effectively, yes, exactly. This is really an algorithm to produce an affine model, and then, but not just, organized by equivalence classes of parallel lines, which we then turn into a projective geometry by just going boop, 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 and then zoom. Yeah. Okay, I was like a little bit, I was impressed by this, but like not super impressed, because I already knew how to just draw from hand by hand a pretty decent projective geometry of order 3. Like I don't need line squares for that, man. I just know what to do. That's because, as I talked about on the first day of this class, in which I had a long conversation with Daniel Zhu last Friday, and he got me back up to speed on things, and I've only forgotten some of what he told me since then. This is all based on finite fields. It's not all based on finite fields. There are these things called finite fields. A finite field is a finite set of objects which obey all the field properties. Like there's an inverse, multiplicative inverse, there's an additive inverse, like closed addition, closed multiplication, commutative, associative with respect to each of those things. There's an inverse, etc. Okay, and there is a finite field of every for every prime number, there is a finite field of that order. So there is a, for the number 3, I think I'm saying this right, there is a finite field with just 3 objects. I think I'm saying this right. Okay. This isn't really important. What's important is the ones of order a prime number are sort of like intuitive, because you just kind of draw it, man. You just like change the slope and they all go like how they go. It's the ones where it's a prime power that are extremely unintuitive. I bet if I gave you guys an hour, you would not figure out how to draw a finite projective plane of order 4. Because there is one, but it is like not logical in a certain kind of way. I think so. But what I can do, or I can do if someone hands it to me, is construct a finite projective plane given 3 mutually orthogonal Latin squares. Should I do this right now, or should I just assign this for homework? Homework? Yeah, I think so. Do you guys get this method? Okay, go.
Are you also like tangentially implying that it's not a Latin square, or not a finite projective plane of order 6?
Yeah, so there is no, I've talked about this already, but I think I've been vague all the other times too. There is no, and someone like, can you just like Google this really quick and fact check me that I'm not saying this wrong? I'm pretty sure I got the gist right, but I might be saying my thing wrong. So it has been proven that there are finite fields of any particular, it has been proven that for any prime or power of a prime, 4, 9, 27, etc., that there is a finite field of that size. Similarly, they have all been proven to be isomorphic to each other. So if there are any 2 finite fields of size 5, they are basically the same field, just the structure is exactly the same. So you might as well refer to the finite field of order 5. But with, and it is conjectured strongly, like they really think it's true, but they haven't proven it, that the only finite projective planes are the ones with order prime or power of a prime. But they are not all isomorphic to each other. There are, like given a finite projective plane of order 5, so that there would be then, I guess, 25, 31 points, if I did that right. There are several, or that might be wrong. You might have to go up higher. But if you go up like not that high, I can't remember how high you need to go. I think it might already be 9. There are multiple like non-isomorphic finite projective planes of that same size, but they're not just the same plane. Have we used the word isomorphic in this class? We will later. It means that they're like different, man, like actually legit different. Okay, so yes.
A lot of things I don't understand here, but the characteristic of any field is the 0 or prime. So
Yeah. Okay, I pretty much got to it. I literally just spent an hour this morning reading this. I know what I'm talking about. But that's not really important. What is important is there's a hell of a lot we do not know still about finite projective planes. The arrow goes in one direction only. If there is a finite field that exists for a certain number, then you can make a projective plane of that order. But there are also projective planes which do not correspond sort of in structure to the finite fields. Yes?
So if you're trying to do core 4 lines to create a field, then like it's something like you can't choose 3 from the same one, and there's probably like something else about like which ones you choose it from. But basically, like there's some way where you can choose a certain number from each square, right? And that'll give you your core 4 lines, no matter what. Am I thinking of that right?
Don't know exactly what you're talking about.
Like, because, I don't know, I'm just thinking, at first I thought it was like core 4 take 1 from each, but that's definitely not true because you can take 2 from the same one, I think. But like, the like core 4 lines.
The core 4 points and the core 4 lines just assert the existence of such a 4. That doesn't mean that there's just uniquely one. For example, these 4 are satisfy the core 4, but so do these 4 points.
Yeah. No, what I'm saying is that like to find a set of 4 lines which satisfy a core 4, I think like you obviously can't choose 3 from the same line square, right? Because they will all intersect. But there's like probably I just feel like there should be some way you choose like a certain like one.
You're trying to verify FPP3. Is that what you're doing?
No, I'm just thinking about it. Like you could choose probably like 1 from each, and would that guarantee you to get a core 4? I don't know, it wouldn't. But if you're choosing like which specific rows or
wait, I don't fully understand, so I'm going to ignore your question and push on. Because the push on is also exciting. It's the reverse algorithm. What do you do when you have a finite projective plane and you want to extract from it a set of mutually orthogonal Latin squares? Now, this is arguably more practical. I don't know. Let's go. Again, I'll do the easy one in class. You're going to do the hard one for homework. Ready? Break of the following. So, okay, the question is, how is the finite projective plane sort of given to you? Suppose it is just given to you as like sets of points. That sounds pretty hard. Okay, so let's go. I now present you with, can you stop at that car maybe at some point? Good. Woo! I now present you with 17 lines. And just trust me, man, these 17 lines, each containing 4 points, are 17 lines of a finite projective plane of order 3. No. Yes. You say nasty, I say beautiful. No, that's really not.
no.
Not yet. Yeah, of course you can. Woo! Alright. Not
17 lines.
do like other stuff today. Yeah. I think that's right? Because 12 and then wait. Because 9 and then I think I'm not 17 lines. Sorry. 13 lines. Good. So it's good to be right. 13 lines. Wait, is that even true? 13 lines. Yeah, because now I need the one more line. Alright, so this could in principle be like hard, depending on how weird the information was given to you. So like, just imagine someone gave you, do you agree that this is bordering on the most abstract way in which you could be given a finite projective plane? How might it be even potentially worse?
get
It's all in
points
binary.
and say what lines they're on.
Okay, yeah, it couldn't be much freaking worse, I guess, is what he's trying to say. The points could be given to you, the names of the points could be like, not necessarily the numbers 1 through 13. That was all I was going to say
That's
there,
really-
right?
That's
Okay.
kind of what
Really bad.
That's borderline, right? Okay, so step one, if you're just handed a list, I claim that that's like the minimum that you need in order to say that you even have a finite projective plane model, is a list of points and a list of what points are on what line, which is effectively giving me a list of lines. Can you guys back me up on this? Okay, so perform a relabeling of points if necessary, such that your points are labeled 1 through 13. Okay? That's always doable.
This necessarily.
Okay, then you end up like here, right? Now, we get to like the first step of the algorithm proper. Arbitrarily designate a line as being the line at infinity.
Arbitrarily.
I believe, per our sort of conversation from 40 minutes ago, right, that there's no such thing really as the line at infinity. Any line can be thought of as a line at infinity. That's what makes the finite projective plane so like sort of symmetric. Okay, so any line could be the line at infinity. Now, the way I have listed these lines strongly suggests that I have a particular interpretation in mind, which is to think of this as being the line at infinity. But like, if you want to be weird and like challenge me to do it some harder way, I will. It's just going to be harder.
9. No.
No.
Give
No,
it
10,
a
11, 12, 13.
Okay, good. Alright, but I claim that it's like no harder to do it any other way. In fact, I might even do it both. Alright, so let us, wait, this is like kind of deep, and I've never taught this before so well as I'm doing now. So, good.
So well.
Woo! Take, what's,
We're just talking about how, it's going to be a lot harder if we pick any other one. And you're like, I claim it'll be the same amount of hardness if I pick any of them.
good. I'm cracking you up for weird meta reasons. Alright, good. Good. This proves that to be funny, you don't have to make jokes. You just can just be weird. People will laugh at you. Alright, good. Let this line be the line at infinity. Well, note, if this is the line at infinity, then what really am I saying? What I'm now saying is that each of these points in this line are points at infinity. Which is to say, this sort of like induces a classification into equivalence classes of parallel lines. And now, by this arbitrary choice, are you paying attention? By this arbitrary choice to make this the line at infinity, what that now says is that every line that has a 10 in it is to be thought of as a line that's like parallel.
Oh, they're exactly
Yeah. So all Stav said at this point is like, turn it into a grid. That's all he said. I'm like, Stav, it's not an algorithm. But it kind of is. It's just a not very fleshed out algorithm. Because now, what we are going to do, essentially, is, so let's, once again, arbitrarily designate, so let's just arbitrarily designate 10 to be the, say, the point at infinity for the equivalence class of horizontal lines. And let's just arbitrarily designate 11 as being the equivalence class, the point at infinity for the equivalence class of the vertical lines. Suppose I try, how do I want to do this? Yeah, so suppose I were to just write out the points 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that how I want the points? I think it isn't quite, because what do, so the 3 lines with 10s in them all look good, yeah? Because line 1, 2, and 3, line 4, 5, 6, and line 7, 8, 9 will all meet at this point 10. Agree? But now, the other one's kind of like ugly or whatever. Because now 11 is supposed to be the point at infinity for the equivalence class of vertical lines. But like this 159 is like not vertical like it's supposed to be, yeah?
What if you make
Say
like-
that that's the
Yeah, so I need to like do a little zoom zoom. So wait, hold on. 159, 267. Do you see how it's like not working, right? And 348.
No, wait. This is like fine. Just like
It's fine, just kind of like unfold it and make it right,
No.
right?
You could
What?
also make
just say
12
11 is the one
or
for
eight
the ones that are parallel this way with slope -1.
But I think you might be able to have it so that none of them are ever.
So, but now what I intend to do is there's no one that told me I had to draw my grid that way, right? So the big brain stop way of doing it, where he just says make it a grid, is to just go 1, 2, 3, 1, 2, 3, and now let's just write 5 here and 9 here. Hi, Stash. Glad you're here. And now 267 goes here. And now 348 goes here. So this is, we've been discussing the stop method. Stop, is this essentially the method?
I've seen 30 seconds of it so far.
Yeah, I mean you start with your 13 lines.
Don't you have
You-
a class?
Kind of.
You arbitrarily pick a line as being the line at infinity. Then each of the points in that line then become the points at infinity. Then that organizes your line into equivalence classes of parallel lines. Yeah.
Yes.
Then the only direction you gave me for this next step is put it in a grid. But that's like bordering on not an algorithm. But I think this is kind of what you do, right? You arbitrarily now designate a point as being the equivalence class for the horizontal lines.
Yes.
And then you just kind of like make them horizontal based on that, right?
Yes.
And you make them vertical. And now that we've done this, now it's okay. So I'm glad you're here for this part, because this is the part where it gets kind of weird. I practiced this explanation this morning, but I might have forgotten it since then. So this is like point 10, yeah? And then we have point 11 down here. And now that they're like drawn nicely, now everything's like good. Because now I just read off, so I've taken care of these first like 6 lines, yeah? And now, well, what about point 12? Point 12 is another point at infinity. And so any line with a 12 in it is to be thought of as a parallel line. Okay, well, what are the lines that have a 12 in it? Well, 147 is one of them. Uh, 258 is another one. And 369 is another one. So, whoop, and then they meet, and they meet at 12. Is that cool? And then we do it with the last point at infinity, 13. That appears in 3 lines, and so those 3 lines are all parallel. And so we get 168 is a line, cha-cha, 249, la la la, and 357, la 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 la. What's up? It makes it, sure it does. Okay, and these are all meeting at that point, which is point 13. And then, of course, you have your line through the, what's up? No, it's beautiful.
No, mine.
Oh, yours.
Looking at this now, there's no way it's gonna help. I'm trying to study there.
These notes?
Yeah.
Okay, so wait, now is the part where supposedly, not only is this method simpler, if you read what Gossett does, you will not believe it. He has this 17-step process that involves taking things and converting them into charts and then converting those charts into new charts. And he has this entire convoluted variable renaming system which enables you to like shuffle and like circularly permute certain points in certain conditions, which effectively is just the untwisting argument that we just made, yeah?
Yeah,
I
last
did
year
appreciate
the
that.
explanation of the algorithm took 30 minutes.
Yeah.
And like by minute 15, no one knew what was happening. They were just following
Yeah,
along.
including me, and then we never even proved that it worked. But I believe that this method is so simple and transparent and true to like the heart of what's really going on that we should now be able to make a relatively simple proof, hand-wavy proof, that this method is even correct. And we're going to send this video to Gossip, who we're friends with now.
So we can insult it. That's how friends work.
Yes, we are friends with gossip.
I love Gossip.
You know you're good friends.
Good, wait, Sal, I'm glad you're here for this part. So, why, wait, this is like, this should be the most exciting part for you, like the argument of why it works. Like there's a lot of understanding that can happen now at this moment. Why does this algorithm produce? Oh, I haven't even got the freaking squares yet. Thank you for reminding me that I need to get the squares. How do so far I've just drawn pictures. I need to extract the squares from the things. Well,
Can you just mod it by 3? Or by 3 and then add 1 or something? I don't know.
no, but I want to take it directly from the model. So far I haven't done it, sorry, I lost my train of thought. I haven't done anything yet, I just like drew the model in a particular way. But but basically essentially what we've done is by forcing the points to be in a grid format, a 3x3 grid, we have sort of made the horizontal lines and the vertical lines, and then the non-horizontal, non-vertical lines will just make a line square. One of them comes from, well, you just put 1s in all those 3 spots. The number doesn't matter. So 1, 1, 1. Another line comes from, maybe it's best to kind of like square it up first. So cha-cha-cha, am I still in frame? Someone check. So 1, 1, 1. Then
yeah,
let this be 2, 2, 2. Does everyone see where these 2's came from? From this line, this red line, which goes through 2, 4, 9. It totally doesn't matter, right? Because if you have a particular line square and you permute all the numbers, it's still a line square, and it's still going to be orthogonal to another square that it was orthogonal to, because you're just, right, because the order pairs won't repeat. That's a kind of a key idea. I'm going to mention that in the end when I'm done. Oh, la la la, and then where are the 3's? Well, then there's a 3 and a 3, 3. Okay? So that's what that first equivalence class, the reds, that met at no, that was the second one, the ones that met at 13. What about the equivalence class of parallel lines that met at 12? The blue ones. The blue ones, again, and it's totally arbitrary what goes what. 1, 1, 1, and 2, 2, 2, and then 3, 3, 3. And I claim now that these 2 squares are a set of mutually orthogonal Latin squares. I shall now defend this claim. First, they are Latin squares. Why? Well, this is the exciting part. I think this is really exciting. Why must they even be Latin squares at all? And you have to argue from the algorithm. You can't just look at the picture and be like, well, they are. No. Well, you tell me.
Okay, so let's just take the 13 one, the red ones.
Okay, he's taking which is this, I sort of did it slightly backwards. This Latin square was the one associated with the red lines, and this Latin square was the one associated with the blue lines. So he is referring to the first Latin square, which is the red lines, okay?
So for it to not be a Latin square, you have to have 2 of the same number in the same, let's say, row, or we just rotate it together. Then you would have to have it contain 1 and 2 or 1 and 3. Right, one of the red lines have to contain 1.2 or 1.3.
Okay.
In order for it to not be a Latin square, because that's repeated. But then you would, since there's only one line through any pair of points, and one of those black lines already goes through 1 and 2 and 1 and 3, then that would just be the same line, and we know that we have to have distinct lines, because this is, yes.
Yeah, you're phrasing it negatively, but I think it's more clear to go in the forward direction, right? Take the but you're right. Okay, so take the red lines. Now wait, hold on. Take the horizontal lines. By the horizontal lines, I mean the 3 lines which meet at point 10, yeah? Note that this is a model of the finite projective plane. What do I know about the model of the finite projective plane is that each pair of lines meets at exactly 1 point. And so, since this line 10, well, again, I think we can achieve sort of deep understanding by not just extracting the two Latin squares from the reds and the blues, but also extracting the Latin squares from the, what square comes from, what's up?
The horizontal and the vertical one.
Yeah, so what's the horizontal one? What square do you get out of the horizontal one? Yeah, you just get the 1, 1, 1, 2, 2, 2, 3, 3, 3 square, and this is the horizontals. Again, because you just assign the same number to a bunch of points if they're on the same line, right? And then the vertical lines, if you assign the same number to all the points on a line, then you get 1, 1, 1, 2, 2, 2, 3, 3, 3. And so really, these four squares are orthogonal to each other. We already had this conversation. And so by sort of, in some ways, it's like being a Latin square is by definition just being orthogonal to these two Latin squares. Is that a good way of putting it?
Yeah, it's true.
Yeah, it's just true. So it is a good way of putting it. And when you go on like fancy places like Wikipedia or others, they will like abstract away. This is what Daniel wanted me to do. I'm glad I didn't listen to him because I didn't understand him. Is to like abstract away from the squareness of the squares and just be like, look, man, a Latin square is just a sort of tuple of like what row you're in, what column you're in, and like what number is in that spot or something like that, right? And it all sort of just permutes in any which way. Yes.
Wait, so those bottom two are like not Latin squares, but they are like orthogonal.
They're not Latin,
squares.
exactly. They are not Latin squares, but they are orthogonal. They are squares which, via the algorithm, are necessarily orthogonal to the other two squares. But I haven't actually defended that yet, so let me just do that now. But basically by the algorithm so far, the one that we sort of followed, which is to like force it to be a grid, guarantees you this square and this square as being two of the squares that come from the horizontal and vertical lines. Now, why are these two squares, say, orthogonal to each other, which is equivalent to the defining property of a Latin square that that the number 1 appear exactly once in each row, right? Or each number.
Row and column, right?
I think, is it column or row?
I think both.
No, but for these two specifically.
Oh yeah, sorry.
Yes, if you're just looking at this Latin square, the first one we extracted from the red lines, and this particular square, right? What does it mean to say that these two are orthogonal to each other? Wait, I lost my train of thought. To say that these two are orthogonal to each other is equivalent to saying that this is a Latin square with respect to its property that the numbers appear exactly once in each row. Right? Because here the number 1, all the numbers in this row are the same. And so to say that it's orthogonal to this square is to say that there are no ordered pairs that repeat. Which is to say that we don't get like 1, 1, 1, 2, 1, 3. If they repeated, that would mean that there's like the numbers were appearing more often than once in each row. Right? So it's the row property of Latin squares, which is equivalent to saying it's orthogonal to this. And it's the column property of Latin squares, that each number appears exactly once in each column, which is captured by saying that these two are orthogonal. Okay, but why are these all orthogonal to each other? It's FPP 2, or 1, 2, FPP 2. FPP 2 says that two distinct lines meet at exactly 1 point. Well, if two lines meet at exactly 1 point, then if you take any line from the horizontal equivalence class of lines, and any of the red lines, they're guaranteed to meet exactly once. Yeah, wait, stop, help, I'm stumbling, I haven't practiced this enough times for it to be totally
I just phrased it
fluid.
as like, you get a bunch of Latin squares, including the two at the bottom, the horizontal and vertical. And each of the Latin squares you get is orthogonal to each other, because each pair of lines from different classes intersects once. Like, orthogonal means you have like one ordered pair ij for each I and j.
Wait, subscripts. Wait, you can come up, but it's exactly what I was just saying. I just wasn't saying it with confidence. Yes, so it's like, right, what would it, yeah, now I'm almost reverting back to your explanation, right? What would it mean if they sort of weren't orthogonal? Well, if they weren't orthogonal, it would mean that you had the same ordered pair appearing twice, right? Right, but if the only way for an ordered, okay, take the red square and the horizontal square, right? They are orthogonal, I claim. Why? I'm kind of going back to your way of doing it now, right? Well, if they're not orthogonal, what does that mean? That means the same ordered pair appears twice, right? When you superimpose the two squares. But for that to be true, since that would mean that
Like an order.
The red lines and one of the black lines
would
share
have to
two
meet
points.
twice, yeah.
Like the way I think about it is an ordered pair corresponds to two lines from different equivalence classes. So if an ordered pair appears twice, those two lines intersected twice. But each pair of lines from different classes intersects exactly once.
Yeah, it's actually this explanation is the most powerful when justifying that the red and blue are in fact orthogonal, right? The red and blue are in fact orthogonal Latin squares because the only way for them to be not orthogonal is if they're an ordered pair repeated. But as these numbers are all collinear, right? Any three 2s all came from the same line. And any sort of three 1s all came from the same line. So if the ordered pair 2, 1 appeared twice, then that would mean that this line of 2s and this line of 1s intersected in two different places. But you cannot have a blue line and a red line intersect in two different places because it's built into the axioms of the finite projective plane that every two lines meet only once. Anyone want to try to say that better / again? That was pretty good, I think, right?
Well, I think sort of it's not any more useful proving that blue and red are orthogonal than it is proving that they're both Latin squares, right? Because you treat the other two as just other squares that they are orthogonal.
Yeah. If the most general way to do, or the almost most general way to do it, is kind of what Stav is suggesting, and what I did, but I sort of backed away a little bit, which is to say that really. Forget about the Latinness of the squares. It's really just it's what this algorithm really produces is 4 orthogonal squares, 2 of which are canonically these specific ones, which guarantees, based on the property of orthogonality, that they are Latin squares. And sort of side note, they're also orthogonal to each other. Follow? Is that a good way of putting it, Ish?
Yeah.
Yeah. Go on.
I was wondering, if this is nice, how many orthogonal squares, Latin squares, are there? To any one Latin square?
Yeah, well, so if it's order 3, or if it's a 3 by 3 Latin square, you can have at most 2, right? Okay, and there's actually even a little proof in gossip that sort of says, hey, I think we skipped it or we went through it really quickly, which says that look, so remember this conversation you and I were having 10 minutes ago where we were like, dude, given any pair, and this is sort of relevant to the